down to theorem number 7 to theorem 18. But before anything else, I would like to emphasize these two key points, the important key points. First is the parallel lines, and second is perpendicular lines. Parallel lines are lines that do not meet, however they are extended to its opposite sides. Next is perpendicular lines. Perpendicular lines are usually lines that do intersect and form four right angles. Come on!
I have there the illustration to illustrate theorem 7. Given these two lines and the floor as my plane. So I have to prove that these two lines are parallel if they are perpendicular to the floor, which is the plane. So to prove that these two lines are perpendicular to the floor, I have to measure the angle that is formed to the intersection of this line and the floor if the measurement is 90 degrees. So therefore we can say that this line is perpendicular to the floor. So I have this protractor which is used to measure the measurement of the angle, to which we can prove that if we measure this one, it will have a measurement of 90 degrees. So we can say that this line is perpendicular to the floor, and true with this line also. So I have the protractor. Okay, if we put the protractor in the floor, and we can see there that it forms 90-degree angle. So therefore we can say that this line is perpendicular to the floor. True with this another line also. So we can say that these two lines are perpendicular to the floor. So we put the protractor, so it clearly gives us a 90-degree angle, or it means that it is perpendicular. So therefore we establish that two lines are perpendicular to the floor. So therefore we can say that if two lines are perpendicular to the same plane, they are parallel.
For theorem 8, let us consider this wall as our plane. And let us have this line as a line parallel to that given plane. The line and the plane is parallel because, however they are extended, they do not meet. Now, I have here the second plane, this plane, which contains the line parallel to that given plane. This plane and this plane intersect to this line. This is now the line of their intersection. Now, since it is said that a line parallel to a given plane is also parallel to the intersection of any plane with a given plane, therefore, this line is also parallel to this line, which is the intersection of this plane and this plane that contains this line.
My heart beats out of time.
I have there the illustration to explain your line. Considering this floor as the first plane and the ceiling as the second plane. And this is the line which to be proved that is parallel to this plane, that this plane can be said parallel to those planes in the ceiling. So I have there the axiom 3. Two distinct planes cannot meet in one point only. So this plane meet this line at only one point, and one point, this point, and the ceiling meet this line at only one point. So therefore, these two planes, which the floor and the ceiling, didn't meet, right? Because as said by axiom 3, that two distinct planes cannot meet in one point only. So therefore, if these two planes didn't meet at any point or at one point only, so these planes are parallel, because a parallel plane rather are planes that, however extended, they will not meet.
For theorem 10, let us have this line and this line. And these two lines intersect at this point, their intersection. Now, this floor as our plane is determined by that intersecting lines. Another plane we have is the ceiling. Now, the ceiling is parallel to these intersecting lines because they do not meet, however, they are extended. Since this plane is determined by the two intersecting lines, then the ceiling and the floor are parallel planes because the two intersecting lines lies wholly in the plane which is the floor.
I have there the illustration to explain Theorem 11. I have there the point, that point which is not on this plane, which is the floor. So I have there two intersecting lines which determines this floor. And I have there a line which is drawn perpendicular to that point. So why I said this line is perpendicular to that floor? Because that two intersecting lines meet this line at one point. And this is supported by Theorem 3. If a line is perpendicular to each of two intersecting lines, it is parallel to this plane of this line. So I am only considering that point on the ceiling and this plane, which is the floor. So I can say now that this floor and that point is parallel because I have been proven that that point is perpendicular to these two intersecting lines by this line, and so in the same manner with this floor. So Theorem 11 has been proven.
Before we will have a proof for Theorem 12, I would like you to know what skew lines are. Skew lines are lines that do not meet but are not parallel. So I have here an example of skew lines. This line and that line over the ceiling. However, they are extended to opposite sides, they will never meet. Now, Theorem 12 says that through one of two skew lines, there is one and only one plane parallel to the other line. So I have this plane, which is the floor. Since it is said that one plane parallel to one of skew lines, I have these skew lines here, right? I pointed it out as one of my skew lines. Now this plane is the only plane which is parallel to that skew line of mine. Through Corollary 1, number 90, that states that if a line outside the plane is parallel to some line of the plane, then the first line is parallel to the plane. Then I have here, no? So we have the plane, which is the floor. It is said that if some line of the plane, so I have this line of the
I have there the illustration to prove Theorem 13. I have this two intersecting lines, or what we say two non-parallel lines. Because if you say parallel lines, there are lines that, however extended, they do not meet. So I am calling this line as non-parallel lines. So I have there the plane, that ceiling is my plane. So therefore, I have to prove that these two non-parallel lines is perpendicular to the plane. For what reason would I be stating? I have there Corollary 191 rather, that says if a plane is parallel to a given line through any point in the plane, there is a line in a plane that is parallel to this given line. So I have stated there my reason to prove that these two intersecting lines is parallel to that plane, which is the ceiling. So therefore, of what I have stated, these two non-parallel lines is perpendicular to the ceiling.
For theorem 14, let us have this floor as our first plane and the ceiling as our second plane. So it said there that if two intersecting lines is parallel respectively to two intersecting lines, their planes are parallel and the angle formed by the lines are equal. So in the floor, we could see two lines that intersect. Actually, many lines that intersect. Let us have this line that intersects this line, and this is their intersection. Looking upward towards ceiling, we also have that intersection. This line and that line that intersect. Now, that intersection and this intersection is parallel to each other. And since there are two intersecting lines, the first intersecting lines is in this plane, then the second intersecting lines lie to that plane and the ceiling. Therefore, the first plane, which is the floor, and the second plane, which is the ceiling, are parallel.
The illustration to prove theorem 15. I have this plane, this table. I have the table, and I have their a plane, which is under the table, which is also considered as a plane, and I have there the floor as my third plane. I have to prove that these three planes are parallel through it is perpendicular to this line. So I have there corollary 104, which states if three planes are intercept in equal segments on any transversal line, it is parallel to each other. So I have these three planes, right? As I said earlier, these three planes is this one, and the floor. So I have there a line. This line is a transversal line which passes the three planes. So these three planes are parallel because of these transversal lines, which proves that this line is perpendicular to these three planes, and then it is if the plane is perpendicular to the same line, they are parallel.
Out of control.
What is a dihedral angle? A dihedral angle is an angle formed by two whole planes, two half plane, a whole plane, and a half plane that intersect. I have here an example. This is a plane, and this is also a plane. Now, these two planes intersect at this line. The angle formed by these two planes is called a dihedral angle. How is a dihedral angle measured? A dihedral angle measured by the measure of the plane angle. It is the measure of a plane towards the other plane. For example, these two planes are intersecting. So whatever the measure of this plane towards this plane is the plane angle. And the plane angle is also equivalent to the dihedral angle. How is a dihedral angle being named? The dihedral angle is named by the first plane, the intersection of the first plane and the second plane, and of course the name of the second plane. So I have this as our illustration. These planes do intersect, and their intersection is this line. Let us have this plane as plane M, this line as line AB, and this plane as plane N. So to name its dihedral angle, we have plane M dash the line AB dash the plane N. That is how to name a dihedral angle.
I have this illustration to prove theorem 16. I have this plane 1 and plane 2, which intersect at this common line or common edge. And I have this also plane 1 and plane 2, which also intersect in this common edge. I have to prove that the measurement of the dihedral angle of those two intersecting planes and their plane angle are equal. So the plane angle is dependent on the measurement of the dihedral angle. So whatever the measurement, the plane angle is also the measurement of the dihedral angle. So therefore, in what the measurement of the plane angle in this dihedral angle form by two intersecting planes is also the measurement of the plane angle. And in this case also, the measurement of the dihedral angle is also the measurement of the plane angle. So therefore, two dihedral angles are equal to two plane angles because plane angle is dependent on the
We can do this song.
to prove theorem 17. Considering this plane and plane 1 and plane 2 is the floor. So I have to prove that these two planes are mutually perpendicular. So I have this two intersecting lines here, which determines the plane, which is the floor, and my plane 1 is this wall, right? So through these two intersecting lines, and there is a line in this plane that is drawn, so these two intersecting lines, so it is through theorem 3 that if a line is perpendicular to each of two intersecting lines, it is perpendicular to the plane of this line. So I have this line and these two intersecting lines. So I have to prove that this line is perpendicular to these two intersecting lines so that I can establish that this plane and this plane are mutually perpendicular. So I have this theorem 5, which states through a point there is only one line perpendicular to the plane. So I have this point of intersection of these two intersecting lines. So there is a line drawn from it, which is only one line that can be perpendicular to this point through theorem 5. So therefore, I have been proved that these two intersecting lines and this one line is perpendicular to each other. Then this two intersecting line contains the floor, and this line is also in this plane. So therefore, these two planes.
Last but not the least theorem is theorem 18. It says there that if a plane is perpendicular to each of two planes, it is perpendicular to their length intersection. So let us have these two planes, the first plane and the second plane. These both planes are perpendicular to another plane, which is the floor. So to prove that these two planes are perpendicular to the floor, we are to measure their angle. So we have to use this protractor to measure their angle. So for this plane, we are to measure this angle here. So we can see that it is a 90-degree angle towards the floor. So therefore, this plane is perpendicular to our floor. The second plane is this one. So we are to measure the angle of this plane towards the floor. So we have to measure it here. So it also implies a 90-degree angle. Therefore, this plane is also perpendicular to the floor. Now, since these two planes are perpendicular to the floor, we are to look for their intersection. So these two planes intersect at this line. So this line is also perpendicular to the floor, since these two planes that intersect is perpendicular to the floor.
We're done with theorem 7 to 18. We hope that out of those theorems that we explained can gain some knowledge out of it.
And through the effort that we've done, hope you enjoy the video that we made. I personally thank you for watching.
Thank you.